Welcome to LearnComputerScienceOnline.com, and in this video, we are going to discuss why computer use binary number system. In other words, why computer can understand the language of only zeros and one. This question is also the most important and commonly asked questions in the technical round in many job interview. All of us know that the computer understands the language of only two numbers, and in mathematics, it is referred as binary 0 and 1. The binary number system is a base 2-number system that uses only two numbers, that is 0 and 1, in order to represent any number. You may be wondering why computer use only binary number system instead of using a human-friendly decimal number system with which we are all familiar and use it in our daily life. The computer system use binary number system due to computer system architecture and the microarchitecture of the microprocessor chip. In order to understand the technical reasons why computer understands only binary 0 and 1, we need to first study the computer system architecture. The microprocessor effectively functions as the brain of the computer system. The processor chip is designed to implement the microarchitecture, which defines the set of binary operations supported by the processor. Further, the computer programs are also required to be converted to binary machine code instructions that computer processor can directly interpret and execute. Let us now discuss each of these topics in detail to understand why computer use binary number system at the hardware level. The computer system is an electronic device that can be programmed to perform various user-specified operations. However, the computer system needs to be directed by using a set of instructions called program instructions in binary code. Let us now discuss what is binary number system. In mathematics, a binary number is used to represent any number using only two numerical numbers, that is 0 and 1. And therefore, the binary number system is said to be a base 2-number system. The binary number system is extensively used in the field of digital electronics, mainly due to the ease of its straightforward implementation. The computer system is also a digital electronic device which consists of a number of electronic components. In digital electronics, it becomes very easy to define the two states, that is on state and off state, using the binary equivalent. In order to understand the reasons why computer use only binary code, we need to first understand the computer system architecture and also the microarchitecture of the central processing unit. It is the microprocessor that provides the processing power to the computer system and executes the program to perform any task. The microprocessor is the brain of the computer system, which controls all the components, CPU operations, and the program execution. The software consists of set of program instructions executed by the microprocessor, which directs the CPU to perform the desired operations. The computer programs are written by using a human-friendly, high-level programming language, such as C language, C++, Java, Python, and there are many such languages. However, since the microprocessor executes only binary commands, the higher-level computer program also needs to be first converted to machine code instructions in binary. So, it doesn't really matter which high-level programming language you choose to write the program code, because eventually, all high-level programs are required to be converted to binary code. This conversion is done by using a special program called compiler. This conversion process is called the program compilation. During the program compilation, the high-level programs are converted by the compiler into machine code instructions in binary that can be directly executed by the computer processor. The microprocessor chip internally consists of millions of integrated circuits packed in the microprocessor chip. This technology is referred as very large-scale integration, used in the processor chip. Each integrated circuit inside the processor chip consists of millions of tiny components called the transistors. The transistor is a fundamental building block for all microprocessor chips. The transistors are used as micro-switch inside the processor chip. And therefore, the microprocessor understands only binary language of 0 and 1. The transistor is made up of silicon, which is a semiconductor material. The transistors inside the CPU function as a micro-switch that can be programmed to be in either switched on or switched off state. When the transistor is in on state, it represents the binary number 1. And when the transistor is in off state, it represents the binary number 0. And for this reason, the microprocessor within a computer system can be programmed to execute only program instructions in binary. Another important factor that makes the binary suitable for computer system is the microarchitecture of the processor chip itself. Each microprocessor chip implements a microarchitecture called instruction set architecture. The instruction set architecture defines the set of commands in binary which processor chip supports. The processor manufacturing companies design the processor chip based on the specific instruction set architecture. During the microprocessor manufacturing process, the instruction set architecture is implemented by embedding these set of binary commands right into the processor chip. The microprocessor can decode the program instructions as per the corresponding operation code, called opcode, and operate on the data, called operand, to perform the desired operation. And therefore, due to this architectural constraints, the processor inside the computer can interpret and execute only binary commands. Now, let us summarize the conclusion. The computer uses binary number system because the processor inside the computer can execute only binary commands. The microprocessor chip implements a microarchitecture in terms of instruction set architecture. The instruction set architecture is a set of binary commands that processor chip supports. And these commands are hardwired into the processor chip. The microprocessor is the main component in a computer system that executes the program and performs the desired operations as per the instruction set architecture. And for this reason, the computer uses binary number system. That brings us to the end of this video tutorial. And in this tutorial, we have discussed why computer use binary number system. Please visit our website, learncomputerscienceonline.com, to learn computer science online. If you have liked this video, then please give us a thumbs up, and consider subscribing to this channel. Thanks for watching, and I will see you soon with another computer science tutorial.
Hey guys, how's it going? In this video, we're going to be taking a look at how to understand binary and hexadecimal numbers. Understand binary and hexadecimal how binary and hexadecimal numbers work is to first understand how base 10 system works that we use on a daily basis. Base 10 system works that we use on a daily basis. I mean, and whenever I say base 10, I mean 1, 2, 3, 4. If I was to write out, then you can look at that number and you know that it's 1,234. 1,234. But let's look at why that is and how we get that number. That is and how we get that number. If we look at this, we know that the 4 is in the ones place. If we look at this, we know that the 4 is in the ones place. 2 in the hundreds, 3 in the tens place. 2 in the hundreds, and a 1 in the thousands. So if I write this out to where you can see that the 4 is in the ones place, you can see that the 4 is in the ones place, 1 in the thousand, 3 in the 10, 2 in the hundred, so 1 in the thousand. Our result down here, of what's really happening is we are taking the value in the thousands position, taking the value and we're multiplying it by 1,000, and we're multiplying it by 1,000. So erase that. So we have 1 times 1,000, which is 1,000, times 1,000, which is 1,000, and then we're adding that to the next position, which is the 100th position, to the next position, which is the 100th position, is 2. So 2 times the value in that position is 2. So 2 times 100 is 200. And then we move on to the next position, 10. And then we move on to the next position, 10. 3 times 10 is 30. And then down to the ones position, 4 and then down to the ones position is 4. 4 times 1 is 4. When we add all those up, we get 1,000. When we add all those up, we get 1,000. Now, this might seem self-explanatory to you guys because this might seem self-explanatory to you guys on a daily basis. But let me show you how it relates to understanding binary and hexadecimal. So our positions here, the thousands position, the hundreds position, and the one, the hundreds position, they can actually be rewritten. They can actually be rewritten. Make these shorter because if we were to expand this out to the millions position, then that'd be a lot of zeros to write in there. Millions position, then that'd be a lot of zeros to write in there. That using exponents. So we can actually rewrite that using exponents and paste this up here. And paste this up here. Okay, so now these are the exact same values, but using exponents instead. So 10 to the 0th power instead. So 10 to the 0th power is 1. 10 to the second power is 10, which is 10 squared, or 10 times 10, which is 10 squared, or 10 times 10. 10 to the third power is 100. 10 times 10 times 10 to the third power is 10 times 10 times 10. And so now we could calculate this just the same way that we did before. And so now we could calculate this just the same way that we did before. 10 to the third. Plus 2 times 10 to the second, plus 3 times 10 to the first, plus 3 times 10 to the first, 10 to the 0, plus 4 times 10 to the 0. So the reason that this is called base 10 is because this is called base 10 is because if you look the exponents at the base, there's a 10 here. The exponent, so there's a 10 here. That's how it relates to binary and hexadecimal. That's how it relates to binary and hexadecimal. Binary, we just whenever we do switch out this binary, base 10, we just for a base switch out this base 10 so let me go down base 2. So let me go down here. Understand this a little bit better. Understand this a little bit better. Let me paste these in. Okay. And then 2 to the 0th power is still 1. To the 0th power is still 1. Is 2 to the first power. 2 to the second power is 2 times 2. 2 to the second power is 2 times 2. 2 to the third power, 2 times 2 times 2. 2 to the third power, 8. 2 times 2 times 2. Okay, is 8. And so let's go ahead and look at a binary number here. So let's go ahead and look at a binary number here. Let's do, and then let me fill in these spots here. 10. 1, and then let me fill in these spots here. 1, 0, 0, 1. And 0. Now we just calculate this the exact same way. Now we just calculate that this the exact same way that we calculated base 10 number. We do base 10 number 1 times 10 to the third, which 1 is equal to 10 to the third. So we have 8 is equal to 8. So we now this is a 0 here. So no matter what we multiply this with, and now this is a 0 here. So no matter what we multiply this with, it's going to be 0. Plus 8 plus 0 times 2 to the first, which is times 2 to the first. So 8 plus 2. So 8, which is plus 10, 2, and then 10 plus 0, which is 10, and then 10 is plus 0. So this is 0. 10. So this in 10 decimal or base 10 is equal decimal or base 10. Okay, and let's do one more quick example here. Okay, and let's do this time one more quick example. 1. This time let's do 1, 1, 1, 1. And let me fill these in. Okay, so now when we calculate this out, okay, it is so now when 1 we calculate this out, 2 to the third, which is 8. 1 times 2 plus to the third, 1 which is 8 times 2 to the second, plus which is 4 times 2 to the second, 1 which is 4 plus 1 times 2 to the first, which is 2 plus 1 times 2 to the first, which is 2 times 2 to the 0th power, which is times 2 to the 0th power, 8, which is 1 plus 4. So we have plus 2, 8 plus 4. So 1 plus 1, 1, 1. So 1 in decimal, 1, 1. See, that'd be 12 in decimal. 14, 15. See, that'd be 12. 14, 15. Now, once you understand how to do these calculations, how to plug in any number here for your base. Then you can plug in any number here for your base. Hexadecimal is so for example, 16. Hexadecimal is base 16. What's confusing about hexadecimal and what trips people up whenever they're looking at it for the first time people up whenever they're looking at it for the first time. Base 16, how do you represent base 16 numbers how do you represent only a single 16 digit? Numbers using only a single digit. Because we only have 0 through 9. Because we only have 0 through 9. Carry over into the alphabet. Carry over, for example, here, the alphabet. If I had, so 8, for example, here, 9, if I had, and then 8, instead of starting back at 0, and then Instead of starting back at 0, it carries over to A, which is 10. In hexadecimal, it carries over to A, which is 10, 12, B, 11, 13, 12, B, 14, D, F is 15, E, 14, and then it carries back over to 0 because it's base 16. So then it goes to 0 because it's base 16. So then it goes to 0. So let's take a look at this, how we would calculate. So let's take a look at this, how we would calculate hexadecimal value. So let me copy hexadecimal value. So let me copy this. So now we're using base 16 instead. So now we're using base 16 instead. Now these values here, I already got them copied out here. Okay. So 16 to the 0th power is 1. 16 to the first power is 1. 16 to the first power is 256. 16 squared is 256 times 16 and 16 times 16 40 times 16 is, and let's go ahead and work through an example so we can see what this is like. Let's go ahead and work through an example so we can see what this is like. Say we had a hexadecimal value. So say we had a hexadecimal value that was 5. So let's go ahead and write this out up here. B. So let's go ahead and write this out up here. B. 5. 5. A. Okay. 5. So 5. Now to start off, we have B, to start off, if you remember, A was 10. B, which if you remember, 11. A was 10. So B, which is 11, times 16, which is 11. Times 16 to the third, which is 4096. So 11 times 1196 times 40 plus 96. A, which is 10, times A, 16 which is 10 squared, times 16 squared, so which is 256. So times 10 to 56 times plus 56 plus 5 times 16 to the first, 5, which is 16, times 16 to the first, which is 16, 5, so times 16, 5, times, and then plus 16, 5, times 16 to the 0th power, 5, which is times 1, 16 so to the 0th power, which is 1, so 5 times 1, which is 5, plus 5 equals plus 47701. 477. Just to make sure that we got that right, let's just to make sure that we got that right, let's go to our programming calculator. Let's go to base 16 here. We'll type in let's go to base 16 here. 5 5 B, and then we will switch back over to our decimal, and then we will switch back over to our decimal. 47701, and it gives us 47701. So that was right. So by now you should be able to convert pretty much any number. You should be able to convert pretty much binary or hexadecimal from binary or hexadecimal over into base 10. One example that you might see a lot is whenever you see RGB color values online. RGB color values. So say for example here. So say for example color white, that is if you have the color white, that is FF and FF. This is calculated, and these first two values calculated are these first two values here. The second two values red value, the green value. The second two values here are the green value, and the last two values are the blue value. If you were to convert these over into base 10, then it would just look like. It would just look this here. So this here. We have F, which is 15. We have F, so which is 15 times 16 to the first power, which is 16. 16 to the first power, which is 16 times 16 equals 240 equals, and then 240, F, which is 15, and then times F1, which is 15, which is times 1, which is 15, so 240, 255 plus 15. So a white RGB, color value is actually 255. So hopefully this tutorial was useful for you guys. Hopefully you're now able to convert values. Hopefully you're now able to binary or hexadecimal or binary or whatever base number it is. Hopefully now whatever base number it is. Hopefully now converting that number comfortable into base 10, and you understand how all these calculations work. And you understand how all these. If you guys do have any questions, feel free to ask in the comments. If you guys do have any questions, feel free to ask in the comments. Future videos. Be sure to subscribe for watching.
You might already be familiar with binary. For example, this is 101 is equivalent to 5 in decimal, and that's because this is the 1's place, this is the 2's place, 4's place, 8's place, 16's, 32's, 64's, and 128's. And we have a 1 in the 4's place and a 1 in the 1's place. 4 plus 1 is 5. So this is fine, but how might we represent a negative number? So let's say we wanted to represent negative 5. Well, there's a couple ways we can do that. One way is to take this 128th place, and instead of using that as the 128th place, use that as a sign. So change this to a 1 here to indicate that this is negative, and then the rest of it is the same. 1, 0, 1. And so this would be 5 here, and then instead of this representing 128, it represents that the number is negative, so negative 5. Now, of course, it's important to know how many bits you're working with, right? Because if we're only using 4 bits, then a 5 would be 0, 1, 0, 1. That's equal to 5. But then we're going to use this top bit here. In this case, we're only using 4 bits, so the top bit is this 4th bit, and so a negative 5 might be a 1, 1, 0, 1. And now instead of this being the 8th place, this is actually representing the sign. So this would be negative 5, and this would be 5. So it's important to know how many bits you're working with so that you know which bit is the first bit, and therefore which bit indicates what the sign of the number is. So to keep going with this example, we can look at just regular counting in binary here. Of course, if we have all zeros, 0, 0, 0, 0, that's equal to 0. And then if we have a 1 in the 1's place, that's equal to 1. We have a 1 in the 2's place, that's equal to 2. A 2 and a 1, that's equal to 3. And then, of course, a 4 is 4. A 4 and a 1 is 5. A 4 and a 2 is 6. A 4, a 2 plus a 1 is 7. So that's simple enough. And then if this first bit here is indicating our negative sign, then we can go backwards too. So if we have a negative 1, that's negative 1. A negative 2, a negative 2 and a 1 is 3, and then a negative 3. Negative 4. A 4 and a 1 is 5, with a negative is negative 5. 4 and a 2 is 6, so this is negative 6. And then a 4 plus 2 plus 1 is 7, and that's a negative 7. And so this is our sign bit. And so this first bit is our sign bit, and then these other bits are just our 1, 2, and 4 place. Simple enough. A couple weird things about this, though. One is that you'll notice there's a negative 0, right? Because you can have 0, 0, 0, and then it can either be a 0 in the sign bit place or a 1 in the sign bit place. So you can have, there's a difference between 0 and negative 0. So that's kind of weird. The other thing that is maybe a little bit inconvenient, and we'll look at some other approaches that don't have this problem, is if you try to add these things together, things get kind of weird. So let's say we want to add a 5 and a negative 5. So normally 5 plus negative 5, you would expect to get 0. Simple enough. But here if we look at 5, 0, 1, 0, 1, and negative 5 is 1, 1, 0, 1. If we add these together, 1 plus 1 is 2, which would be a 0 and then carry the 1. 1 plus 0 is 1. 1 plus 1 again is 2, but we'll put that as a 0 and carry the 1. And then here 1 plus 1 again is 2, so a 0 and carry the 1. So in this case, what we're seeing is 5 plus a negative 5 is not 0, it's 0, 0, 1, 0, which, well, and we have a carry. So we have a carry coming out of this 1 bit that we don't, if we're working with 4 bits, we're going to ignore this carried bit. And so we have 0, 0, 1, 0, which is 2. Well, so that's kind of weird. If we're adding 5 and negative 5, we wouldn't expect to get 2. And you can try adding some other things here, and it doesn't work. So let's take a look at another scenario here. This is called 1's complement. What this is again, everything from 0 to 7 is the same. Same as we saw before. And this first bit here is all zeros, so we know that these are all positive. But what we do for the negative numbers is we actually just flip all of the bits. We take the complement of all of the bits. So, 2 here is 0, 1, 0. Well, 0, 0, 1, 0. Negative 2 is 1, 1, 0, 1. So we're just flipping each of those bits. So we flip the 0 for a 1, we flip the 1 for a 0, we flip the 0 for a 1, and so on. If you look at each of these numbers, so 5 is 0, 1, 0, 1, negative 5 is 1, 0, 1, 0. So what happens with this? So we still have this kind of strange thing where we have negative 0, and we'll come back to that in a minute. But what we can do is we can try to add some numbers. So if we add 5, so 0, 1, 0, 1, so that's 5, and negative 5, 1, 0, 1, 0, if we add those adding negative 5 here. What we end up getting is 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1. We get 1, 1, 1, 1, which is negative 0. So that's closer, right? 5 minus 5, you'd expect to get 0. Negative 0 is, I guess, the same thing. So that's pretty good. And that actually works for any of these. We can do 3 minus 3, or 3. So 3 is 0, 0, 1, 1. Negative 3 is 1, 1, 0, 0. So this is 3 plus negative 3. If we add these together, so 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, we get 1, 1, 1, 1 again. And so again, 3 minus 3 is negative 0. So this is definitely doing a lot better than here, where we were saying 5 minus 5 was 2. That's definitely not right. So negative 0, definitely a lot closer. Let's try some other things to kind of see if we can see a pattern here. So if we did, let's say 5 plus negative 3. So 5 minus 3, let's see what we get there. So 5 is 0, 1, 0, 1. And negative 3 is 1, 1, 0, 0. So 1 plus 0 is 1, 0 plus 0 is 0. 1 plus 1 is 2, so we'll put a 0 and carry a 1. And then 1 plus 1 again is 2, so we'll put a 0 and carry a 1. And so if we ignore this first bit here, because we're working with 4 bits, we get 1. So 5 minus 3 is 1. That's close. It should be 2, but let's see what happens if we do, let's say 6 minus 2, or 6 plus negative 2. So 6 is 0, 1, 1, 0. Negative 2 is 1, 1, 0, 1. 1, 1, 0, 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. Put a 0 and carry the 1. 1 plus 1 is 2. So put a 0 and carry the 1. Again, ignore that first bit because we're working with 4 bits. So 0, 0, 1, 1 is 3. So we're saying 6 minus 2 is 3. Close, but we're definitely seeing an interesting pattern here. In fact, if we look, these places where we're getting this negative 0, if we just go down 1, we see 0, which is what we want. Here, 5 minus 3, we'd expect to see 2, but we're seeing 1. So if we just go down 1, we'd actually see a 2. 6 minus 2, we'd expect to see 4, but we're actually getting 3. But if we go down 1, we get the right answer. So we could just always add 1 to each of these. Of course, it's kind of weird to say add 1 to negative 0 to get to 0, but if you kind of bear with me a minute, you'll see that if we add 1 to the binary value and it flips over, you do get to the right thing. And here you get to the right thing. So the ones complement, just flipping all of these bits is close. It's very close. It's off by 1 on all of our arithmetic. And it also still has that nice property that we saw with the sign bit, which is, you can look at this first bit and you can tell these are all negative numbers. And if the first bit is 0, then they're positive numbers. So it seems like the ones complement has a lot of the, a lot of nice properties, that you'd have in the sign bit. The one thing that's, well, I guess it's not too bad, is that to invert or to negate a number, if you're going from 5 to negative 5, with a sign bit, all you'd have to do is flip 1 bit. You just flip that first bit to a 1 and you get to negative 5. With the ones complement, you have to invert each bit. So it's a little bit more work, but of course inverting bits is pretty easy to do in hardware. If we're building hardware to do this, if we're building a computer, it's going to be doing some math. So ones complement seems pretty good, but it is off by 1. So what we can do is look at another scenario, which is 2's complement. And if we compare 1's complement to 2's complement, it's basically the same, except what it does is it gets rid of this negative 0. So instead of having negative 0, we just go right to negative 1. Negative 2, 3, 4, 5, 6, 7. And the kind of weird thing here is we have a negative 8, and we don't have an 8. But the nice property about this is that all of our math works out very nicely. So if we have 5 minus 5, 5 here is 0, 1, 0, 1. And so that's 5. And negative 5 is 1, 0, 1, 1. So 1, 0, 1, 1. And if we add these things, if we add -5, 1 plus 1 is 2, so we'll put a 0 and carry the 1. 1 plus 1 is 2, so put a 0 and carry the 1. 1 plus 1 is 2, so we'll put a 0 and carry the 1. And 1 plus 1 is 2, so put a 0 and we have a 1 that we're carrying. And so you'll notice that each, when we're looking at the negated version of something, when we add each of these place values, we get a 2 each time, and that's why it's called 2's complement. But in any event, you see that we end up with 0, which is just what we would want when we add a number to its inverse. And in fact, you can try it with any of these numbers, and you'll find out that you get all zeros. So let's try, 6 minus 2. So 6 is 0, 1, 1, 0. That's 6. And minus 2 is 1, 1, 1, 0. 1, 1, 1, 0. And if we add these together, so if we add our -2, -2, adding -2 there. 0 plus 0 is 0. 1 plus 1 is 2. So we'll put a 0 and carry the 1. 1 plus 1 plus 1 is 3. So that's a 1 and a carry a 1. And the 1 plus 1 is 2. So 0 and carry a 1. And again, we ignore that 5th bit there. And so 0, 1, 0, 0 is 4. And sure enough, 6 minus 2 should be equal to 4. So this 2's complement works pretty well. And it also has this nice property, again, that first bit is a sign bit, right? Because all of these negative numbers have a 1 there. And what's even more interesting about 2's complement is if you look at the place values, it actually makes sense. This is our 1's place, this is our 2's place, this is our 4's place. And this place here, it looks like a sign bit, but really it's a -8's place. And you can see when we have a -8 and all zeros, we have a -8. But if you have a -8 and a 1, you get -7, right? If you have -8 and a 4, you get -4. If you get -8 plus 4 plus 2 plus 1, you end up at -1. So this bit value actually has a mathematical meaning, which is why our math works out. So it's pretty cool. The one thing that's a little bit harder with 2's complement is negating a number. So if we want to go from a 5 to a -5, it's kind of a two-step process, right? So 5 is 0, 1, 0, 1. The first thing you have to do is take the 1's complement, 1, 0, 1, 0, so flip all the bits. So you're just inverting everything. That's easy enough. But then you have to add 1. So you invert and then add 1. So to add 1 to 0, 1, 0, 1 is just 1, 0, 1, 1. And then this invert, so this is 5, then we invert it, and then we add 1, and that gets us to -5. And you can see -5, 1, 0, 1, 1, 1, 0, 1, 1. So it's a little bit more work to go from a positive number to its inverse, because you have to invert it and then add 1. But what you'll see in the next video when we build a circuit that can add and subtract, you'll see that it's actually not too hard to build this in hardware.
In this video, we're going to talk about how to convert hexadecimal numbers binary numbers into binary numbers. So let's start with this example. A9. How can we convert that into a binary number? Well, the first thing we need to do is convert the A or decimal value, a number or decimal. In the hexadecimal system, A corresponds to 10, corresponds to 10 in the decimal system, corresponds to 11, corresponds to 11, C corresponds to 12, C corresponds to 12, D corresponds to 13, D corresponds to 13, E corresponds to 14, and F corresponds to 14, and F corresponds to 15. So we could replace A with 10. Now, each number and letter in the hexadecimal system, you could represent a binary number in groups of 4. So A corresponds to 10, and we have a 9. And we have a 9. Now, how can we convert each of these into a binary number? So let's start with 9. So let's use the numbers 8, 4, 1 is basically 2 to the 0. 1 is basically 2 to the first power. 2 is 2 to the first power. 8 is 2 to the third power. 8 is 2 to the third power. 9 is the sum and 1 of 8 and 1. So we're going to replace the 8 with a 1. We're going to replace the 8 we didn't use the 4 and a 2. Because we didn't use the 4 and a 2, we're going to substitute the 1. 0. So we're going to use the 1 for 1. So we're going to replace that with a 1. Now let's use the same pattern of numbers. For 10. Now 10 is the sum of 8 and 2. So because we use those numbers, let's replace that with 1. And we'll use a 0 to correspond. And we'll use a 0 and 1 since we didn't use those numbers. With 4 and 1 since we didn't use those numbers. So 10 is represented by the binary number 1, 0, 1, 9 1, 0 is represented by the binary number 1, 0, 0, 1. Now, A9, this entire thing, represents is equivalent to this binary system. So this is the answer. So this is the answer. A sub 9 in the hexadecimal system, that is the base equal to this binary number 1 is equal to this binary number 1, 0, 1, 0, 1. Basically, you just put these two together. And so that's a quick and simple way. A hexadecimal to convert a hexadecimal number into a binary number. Now, just to make sure that we have the right answer, let's convert each of these two numbers into a decimal value, and let's make sure it's a decimal value, and let's make sure it's the same. So let's convert the binary number. Into a decimal number. So the first number we need to multiply by 2 to the 0. And the second one by 2 to the first power. And the second one by 2 to the first power. And then it follows this pattern. So we have 1 times 2 to the 7th, which is just 2 to the 7th power, if you multiply 2 7 times, that's going to give you 128. That's going to give you 128. And then we have a 1 for 2 to the 5th power, which is 32. And then 2 to the 3rd power is 8. 2 to the 3rd power is 8. And 2 to the 0 power, is 1. So we need to add 128. Plus 32 plus 8 plus 1. So this gives us a value of 169. So that's how you can convert a binary number into Now let's convert the hexadecimal number into a decimal number. Just to make sure that it's equal to 169. So we have A9. The first number we're going to multiply by 16 to the second one by 16 to the first, and the second one by 16 to the first. Now keep in mind A corresponds to 10. So it's going to be 10 times 16 to the first times 16 to the 9 times 16 to the 0 power times 16 to the 0 power. 10 times 16 is 160. 10 times 16 is 160. And 16 to the 0 power is 1. And 16 to the 0 power is 1. You have 9 times 1, which is 9. You have 9 times 1, which is 9. And so this adds up to 169. So because these two have the same values, we know that these two are equivalent to each other. These two are equivalent to each other. So this is indeed the final answer. Let's try another example. 3b7. Let's convert that into a decimal number. So we have a 3, and then we said that A, and then we said that A, which means corresponds to 10, which means B corresponds to 11. So let's replace B with 11, and we have a 7. Now let's convert this into a binary number. This looks like it's 21. Let me separate the 2 and the 1. So let me separate the 2 and the 1. 3 is the sum of 2 and 1. So we could represent 3 as the binary number 0, 0, 0, 11 is the sum of 8 of 8 plus 1 plus 2. So this becomes 1. 1, 0. We didn't use the 4, so the 4 is going to correspond to a 0. The 4 is going to correspond to a 0. Is the sum of 4 and 1. 2. So the binary number that corresponds to 7 is 0. 1, 1, 1. Thus 3b7 is equal to, and we could start here. We don't need to start with the 0. We're just going to combine these numbers. We're just going to combine these numbers. So 3b7 in the hexadecimal system is 1, is 1101101110111 as a binary number. Now, let's make sure that we have the right answer. So let's convert the binary number into a decimal number. So we're going to multiply this by 2 to the 0. We're going to multiply this by 2 to the first, and then 2 to the first, and so forth, and so forth. So since we have a 1, or on top of 2 to the 9, or on top of 2 to the 9, which is, we're going to use 2 to the 9, which is 512. And then we have 1 times 2 to the 8, 1 times 2 to the 8, 2 to the 8 is 256, 2 to the 7 is 128, 2 to the 7 is 128, now 0 times 2 to the 6, now 0 times 2 to the 6, so that's going to be 0, and then we have a 1 in front of 2 to the 5th, and then we have a 1 in front of 2 to the 5th, which is 32, and then 1 times 2 to the 4, and then 1 times 2 to the 4, and then 2 squared, and then 2 squared, and 2 to the 0 is 1, plus 2 and 2 to the 0 is 1. So if we add 512 to 128, plus 32 plus 16 plus 32 plus 16 plus 4 plus 2 plus 1. That will give us the number. 951. Now let's convert the hexadecimal number into a decimal. We'll get the same answer. Let's see if we'll get the same answer. So we have 3. So we have B 7. B, so the 7 we're going to multiply by 16. So the 7 we're going to multiply by 16. B we're going to multiply by 16. B we're going to multiply by 16 to the first power. And 3 by 16 squared. And 3 by 3 times 16 squared. So it's 3 times 16 squared. B is 11. So 11 times B is 11. So 11 times 7 times 16 to the 0. And then 7 times 16 to the 0 power. Now 16 squared. Or 16 times 16, that's 256. Or 16 times 16, that's 256. That's going to be 768. That's going to be 768. 11 times 16 is 176. And 16 to the 0 power is 1 times 7. 0 power is 1 times 7. So if we add 768, 176, that's going to give us 951. That's going to give us 951. And so the fact that these two are the same means that we did it correctly. So this is indeed binary value for 3b7. Now let's work on one more example. So let's say we have the hexadecimal number 29D, and let's convert that to a binary number. So feel free to try. So let's separate numbers and letters. So we have 1 numbers and letters. So now we said that A is 10. So B is 11. C is 12. And D is 13. So let's replace D with 13. Okay, for the first one, to get a value of 1, we just need use only this one. So it's going to be 0, 0. So it's going to be 0, 0. So that's the binary equivalent of 1. Now to get 13, we need to add 8. Plus 4, which is 12. Plus 4, and then plus 12. That's going to give us 13. That's going to give us 1101. So 1101 corresponds to get 2. We just need to use this number only. So 0, 0, 1, 0, 0, 1, 0. To get 9, we need to add up 8 and 1. So it's going to be 1, 0, 0, 1, 0, 0. So thus we could say that the hexadecimal number 1D29 is equivalent to everything that we see starting with the first one. So it's equivalent to 1 1 1 1 0 1 1 0 0 1 1 0 0 1 0 0 1 0 0 1. So this is the final answer. So now you know how to convert a hexadecimal number into a binary number. In this video, we're going to talk about how to convert a binary number into a hexadecimal number. So let's start with this example. Let's say we have the binary number 10110111. How can we convert this into a hexadecimal number? The first thing you want to do is separate the binary numbers in groups of 4. So this is the first group of 4, and this is the second group of 4. Now convert the binary numbers into a decimal value. To do so, we need to multiply the 1 by 2 to the 0, and then the second one by 2 to the first power, and then by 2 squared and 2 to the third power. 2 to the third power is 8, 2 squared is 4, 2 to the first is 2, and anything raised to the 0 power is 1. So we have 0 times 8, so that's 0. And then we have 1 times 4, and then 1 times 2, and 1 times 1. So basically, we just need to add up these numbers because they carry a 1 with them. So the binary number 0111 correlates to 7 because 4 plus 2 plus 1 is 7. Now for this one, this is 8, 4, 2, 1. So we're going to add up 8, 2, and 1 because they have a 1 value associated with them. So 8 plus 2 plus 1, that's going to give us 11. Now we need to convert these numbers into the hexadecimal values. 10 corresponds to A, and 11 corresponds to B. So we're going to replace 11 with B. And so we have B7, base 16. So the binary number 10110111 correlates to this in the hexadecimal system. And so that's how you can convert a binary number into a hexadecimal number. Now for the next example, let's say it's 1011101010. Go ahead and convert this binary number into a hexadecimal number. So like before, let's break it up into groups of 4. Now, notice that we don't have 4 numbers here, so we can add 2 zeros. So the first group will be 0010, and then the second group will be 1110, and the last one is 1010. So let's start with the first group. So we have the numbers 8, 4, 2, and 1. So we only have a value of 2 here. For the zeros, just ignore them. So this number, 0010, corresponds to a value of 2. For the second group of 4, we need to add 8 plus 4 plus 2. 8 plus 2 is 10, 10 plus 4 is 14. And for the last one, the significant values are 8 and 2, which will give us 10. Now recall that 10 corresponds to A, 11 corresponds to B, 12 corresponds to C, 13 corresponds to D, which means 14 corresponds to E. We could replace 10 with A. So the answer is going to be 2EA. So it's 2EA in the hexadecimal system. And so that's it. That's how we can convert this binary number into a hexadecimal number. Now let's try another example. 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, 0. Try that one. So let's separate it into groups of 4. So the first group, we're going to add 3 zeros. So it's going to be 0, 0, 0, 1. And then the group in green is 1, 1, 1, 0. And then in blue, 1, 1, 1, 1. and in red 1100. So for this one, only this number is significant. So we have a value of 1. For the second one, the numbers 8, 4, and 2 are important. So 8 plus 4 plus 2, that's 14. And for the last one, all of them are important. So they add up to 8 plus 4 plus 2 plus 1, that's 15. And for the final one, it's just 8 plus 4, which is 12. So we know 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. And so the answer is 1 E F C in the base 16 system. So this is our answer as a hexadecimal. Now, to make sure that we have the right answer, let's convert the binary number and the hexadecimal number into a decimal value, and let's make sure that it's the same. So let's start with the binary number. So this is 2 to the 0, 2 to the first, 2 squared, 2 to the third, fourth, fifth, sixth, and so forth. So we have a 1 associated with 2 to the 12. So 1 times 2 to the 12, that's going to be 4,096. And then we have 2 to the 11th, which is 2,048. And then 2 to the 10th, which is 1,024. And 2 to the 9th, which is 512. And then 2 to the 7th, that's 128. 2 to the 6th is 64. And then 2 to the 5th, which is 32. And then we have a 16, 8, and a 4, which is the last one, 2 squared. So if we add up these numbers, 4,096 plus 2,048 plus 1024 plus 512 plus 128 and all the way to 4, this will give us 7,932. So now let's convert the hexadecimal number into a decimal number. Let's see if we get the same thing. So we have 1 E F C. So we know E corresponds to 15. And E corresponds to 14, F corresponds to 15, and C corresponds to 12. We need to multiply C by 16 to the 0 power, F by 16 to the first, E by 16 squared, and 1 by 16 cubed. So it's 1 times 16 cubed, and we said E corresponds to 14, so it's going to be plus 14 times 16 squared, and F is 15, and then C is 12. Sixteen to the third power, that's 4,096. 16 squared is 256 times 14, that's 3,584. 15 times 16 is 240. And 16 to the 0 power is 1 times 12 will give us that. So now let's add up 4,096, 3,584, 240, and 12. And so this will give us the same answer, 7,932. So that's how you can check your work, which means that this indeed is the right answer. And so that's it for this video. Now you know how to convert a binary number into a hexadecimal number. At the same time, you also know how to convert a binary number into a decimal number and also a hexadecimal number into a decimal number. So thanks for watching. In this video, we're going to talk about how to convert into a decimal number into a binary number. So how can we convert 75? So how can we convert 75 into a binary number? It helps to be familiar with the powers of 2. It helps to be familiar with the powers of 2. 2 to the 0 power is 1. 2 to the 0 first power is 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the fourth power is 16. 2 to the fifth power is 32. 2 to the sixth power is 64. 2 to the sixth power is 2 to the seventh power is 128. 2 to the seventh power is 128. Now we don't need to go further because exceeds 75. 128 exceeds, so the highest number, that is, so the highest base 2 number, that is the highest base 2 number, 75, that is less than 64. 75 is, so 64. We're going to start with 64. Now in this video, I'm going to show you two ways a decimal number to convert a binary number. The first half of the video will focus on the second half, the subtraction method, will focus on the second half, successive division. So I'm going to show you both ways, and then you can pick and choose which method. Now, once you have your first number, which is 64 in this case, let's subtract 75 by 64. Let's subtract 75 so that will give us 64. And so that will give us the highest number. Now the highest number under 11 is 8. 16 exceeds 11, so we can't use that. 16 exceeds 11, so let's put an 8 here. And then let's subtract 11 by 8. And then let's subtract 11 by 8. 11 minus 8 is 3. So the next highest number just under 3 is 2. So the next highest number just under 3 is 2. So let's put a 2 here. And so let's put 3 minus 2 is 1. 3 minus 2. And so the next highest number is a 1. And we could stop. So the next highest number is a 1. And we could stop here. Because if you add these numbers, 64 plus 8, that's 72. 64 plus 8, that's 72. 72 plus 1 is 75. 74 plus 1 these four numbers is 75. Add up to 75. These four numbers, now once you have that, you can begin to write the numbers. You can begin to write binary the numbers. So because we have a 64, we're going to put a 1. So because we have a 64, we don't have a 32, so let's write a 0. We don't have a 32, we don't have a 16, let's write a 0. We do have an 8, so let's put a 1. We do not have a 4, so let's put a 0. We do not have a 2, let's put a 0. But we do have a 2. So 75 is equal to 1001 0. And so that's one simple way in which you can convert into a decimal number into a decimal number into a binary. Now here's another example. Let's say if we have the number 142. Let's say if we have the number, let's convert that into a binary number. So let's write the list of numbers that we're going to work with. 64, 128, 32, 64, 16, 32, 4, 16, 2, and 1. 8, 4, so the highest number under, so the highest number 142, the highest base 2 number is 142, the highest base 2 number is 128. And then if we subtract 148 by, 142 by 28, 142 that's going to give us 28. That's going to give us, and so 14. The next highest number, 14 is 8. Just under 14 is 8. 14 minus 8 will give us 6. So 14 minus 8 will give us 6. Now the next highest number, that's under 6 is 4. So if we subtract 6 by 4, that will give us 2. 6 by 4, that will give us 2. And then 2 minus 2 will give us 0. And then 2 minus 2 will give us 0. So we could stop at and so you could check it. If you type in 128, if you type in 8 plus 4, 128 plus 8, that will give you 142. So make sure that these numbers, so make sure that these numbers, so you want to find all the base 2 numbers that add up to this number. So you want to find all the base 2 numbers that add up to this number. You can convert it into a binary number. You can convert it. So this is going to be 1. So this is going to be 64. Nor do we have a 64 or 16, nor do we have a 32. We do have an 8, a 4, we do have an 8, and a 2, and we don't have a 1, and a 2, and we don't have a 1. So 142 is basically 1. So 142 is basically 1, 0, 0, 0, 0, 1, 1, and so that's how you can convert a decimal number. And so that's how you can convert a decimal number into a binary. Now here's another example. Let's try a bigger number. 339. Let's try a bigger number, 339. Go ahead and work on that example. Go ahead and work on that example. We need a number that's higher than 128. We need a number that's higher than 256. 128 times 2 is 256. So we're going to start with 256. And then we're going to start with 256, and then 64, and then 128, 32, and then 64, 16, 8, 32, 4, 16, 8, 4, 2, and 1. So 256 is the highest number. So 256 is the highest number just under 339. That's just under 339. And so let's subtract. 339 by 256. 339 by 256. So this will give us 83. And so this will give us the next 83. Highest number. The next highest number under 83. The highest base 2 number that's under 83 is 64. So let's subtract 83 by 64. So let's subtract 83 by 64. And that will give us 19. And now let's not forget to write the 64 here. And let's not forget to write now the next highest number under 19. Now the next highest number under 19 is 16. 19 minus 16. 19, so that will give us minus 16. And so that will write the 16. And then the next highest number that's under 3 that's under 3 is 2. 3 minus 2 is 1. So 3 minus 2 is, put the 2 here, 1. And then 1 minus 1 is 0. And then 1 minus 1 is 0 as well. So we need to include the 1 as well. And then check the work. Make sure that make sure that all of these base 2 numbers add up. All of these base 2 numbers add up. And so type in 256 plus 64. And so type in 256 plus 64 plus 16. And that will give you 339. And that will just make sure that you did everything correctly. Just to make sure that you did everything correctly. Now let's write the numbers. So we have a 256. So we have a 256. We do not have a 128. We do have a 64. We have a 32. And since we don't have an 8 or 4, we're going to write. Since we don't have an 8 or 4, we do have a 2 and a 0. So we do have a 2 and a 1. So a 1 means on or yes. So a 1 means 0 means off or yes. And a 0 means off. So this is this. So 339 is 339. 1 0 is equal to 1 0 1 0 1 1 0 1 1 1 0 0 1 1. Now the second method involves successive division. And so let's go over the 3 examples that we did. So this allows us to confirm our answer. So in the first example, we said that 75. So in the first example, we said that 75 is equal to the binary number 1 0 0 1 0. Let's confirm that using division. Successive. So division. Here's what we need to do. Start with 75 and divide it by 2. Start with 75 and divide it by 2. 75 divided by 2. 75 divided by 2. So what this means is that 37. It's 37. So what this means is remainder 1. It's 37. Remainder 1. Now take the 37 and then divide that by 2. Take the 37. So 37 divided by 2. So 37 divided by 2. So that's 18.5. Remainder 1. So that's 18. Then take the 18, divide that by 2. Then take the 18 divided by 2 is exactly 9. 18 divided by 2 is exactly remainder 0. With no remainder. And then 9 divided by 2 is 4.5. And then 9 divided by 2, we say it's 4.5. Remainder 1. So we say it's 4. And then 4 divided by 2 is exactly 2. And then 4 divided by 2 is exactly 2. So it's 2. And then 2 divided by 2 is 1. And then 2 divided by 2 exactly 1. So 1 remainder 0. Exactly 1, so 1 remainder 0. And then finally, 1 divided by 2, that's basically 1 divided by 5, so we could say that's basically 0.5, so we could say it's 0, and then we stop here, remainder 1, and then we stop here. So at the bottom, the MSB or the most significant bit, the MSB or the most significant bit, at the top you have the LSB, or at the top you have the LSB. Now the way you read it is from the most significant bit. It's from the most significant bit, so basically from the bottom to the top. So basically from the bottom. So look at the numbers that we have. So look at the numbers that we have. So we have a 1, and then a 0, 1, and then a 0, 1, 1, which is basically the numbers that we have 1, 1, which is basically the numbers that we have there. So if you write it from bottom to top, it's 1. So if you write it from bottom to top, it's 1, 1, 0, 0, 1, 1, 0, 1. So hopefully you see that. So that's how you can get the same answer. Using successive division. Now let's go over this second example. Let's say we have 142. So let's say we have 142. Use successive division to convert it to a binary number. So let's divide this by 2. So let's divide this by 2 divided by 2 is exactly, so 142 divided by 2 is exactly 71. It's 71 with a remainder of 0. So it's 71 with a remainder of 0. And then 71 divided by 2. And then 71 divided by 2. That's 35.5. That's 35 remainder 1. So it's 35. And then let's take 35 and divide that by 2. Let's take 35 and divide that by 2. So that's going to be 17.5. So that's going to be 17 remainder 1. Or 17, and then 17 divided by 2, and then 17 divided by 2 is 8.5, so that's 8 is 8.5, so that's 8, and then 8 divided by 2 is exactly 4, and then 8 divided by 2 is exactly 4, so that's 4, and then 4 divided by 2 is exactly 2, and then 4 divided by 2 is exactly 2, and then 2 divided by 2 is exactly 1, and then 2 divided by 2 is exactly 0, and then finally, so 1 remainder 1 divided by 2, and then finally is 0.5, 1 divided by 2, that's 0, is 0.5. So that's 0, remainder 1. So we're going to read it from the most significant bit to the least significant bit. From the most significant bit, so from the bottom to the top. So from the bottom it's going to be to the top. 0, so it's going to be 1, 0, 0, 1, 0, 1, 1, 1, 1, which 0. If you rewind the video, which you'll see that we had this answer. You'll see that we had this answer. Now let's work on the last example. So let's divide 339 by 2. So let's divide 339 by 2. This will give us 169.5. This will give us 169.5 remainder 1. Or 169 and then divide 169 by 2. And then divide 169 by 2. And so that's going to be 84. So that's going to be or 84. 84.5 or 84. And then 84 divided by 2. That's exactly 84 divided by 2. That's exactly 42 remainder 0. And then 42 divided by 2 is exactly 21. And then 42 divided by 2 is exactly and then 21 divided by 2, that's 10. And then 21 divided by 2, that's 10.5. Remainder 1. So it's 10. And 10 divided by 2 is exactly 5. And 10 divided by 2 is exactly 5. So 5 divided by 2 is 2.5. So that's 5 divided by 2 is 2.5. And then 2 divided by 2 is exactly 1. And then 2 divided by 2 is and exactly 1 divided by 2 is always 0.5. So and 1 divided by 2 is always 0.5. So that's always going to be 0, remainder 1. So let's go from the most to the least. So starting with the number on the bottom, it's going to be 1, it's going to be 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1. And so this is 339 as a binary number. And so that's it for this video. So now you know how to convert decimal numbers. So now you know how to convert binary numbers. Decimal numbers. You have 2 ways of doing it into binary numbers. You have 2 ways of doing it. Thanks for watching.
From this lecture, we will start number system. From this lecture, we will start number system. Set of values number system defines a set of values used to represent quantity. Any quantity. Let us consider, and this quantity is represented by decimal number 739. We can also represent the same quantity. We can also represent the same quantity like in binary other number system, octal, like duodecimal, hexadecimal. Decimal number system is the most popular number system which we use in our daily life. If we have to measure the distance, weigh something, or measure the distance, weigh something, or count our money, there are 10 different digits in decimal number system. There are 10 different digits in decimal number system from 0 to 9, 2, 3, 0, 1, 2, 5, 3, 6, 7, 8, 9. These are the 10 different digits in decimal number system. These are the 10 different digits. In case of binary number system, we have two different digits for binary number system. Now, what is the base for binary number system? The base of a number system is also called as radix. The base is also called as radix. the base radix, and because of this r, the notation for base, the notation for base. Now the base will tell us how many distinct digits we have in a number system. For example, we have in a number system. For example, in case of decimal number system, we have 10 different digits. Because we have 10 different digits. For binary, we have 2 different digits. Now, what are these 2 different digits? Now, what are these 2 different digits we have to find? Digits will start from 0. Digits will start from 0, and there will be increment of 1 every time, and there will be increment of 1 every time, r minus 1, where r is the base, and in this case, where r is the base, and in this case, r is 2, and in this case, 2 minus 1, 2. This will give us 2 minus 1. This will give us 0. So there are only 2 digits in case of binary number system, and in binary number system, we do not call binary number system, we do not call them digits, and as there are 2 numbers, we call this system. And as there are 2 numbers, we call this system. In case of octal, the base is 8. In case of octal, we definitely have 8 distinct digits. We definitely have 8 distinct digits. They are from octal number system, and they are from 8 minus 1, and this will give us 0. 1, this will give us 0, 4, 1, 5, 3, 6, 4, 7. So these are the digits in case of octal number system. For decimal, we have already seen 0 to 9. For decimal, we have already seen 0 to 9. For duodecimal, the base is 12. For duodecimal, we have the base is 12. So we have 0 minus 1 to 12. This will give us 0, 1. This will give us 0, 4, 1. 2, all the way to 9, and then we have all the way to 9. We represent, and then we have 10 as we represent 11 as A, 11 as B, 13 as D, 14 as D, and 15 as E. This is how we represent 10, 11, 12, 13, we represent 10, 11, 12, so 10 is A, 11 is B, so 10 is and A, we only have 12 distinct digits, and we only have 12 distinct digits, so we will have 0 to 11, B in case of we will have 0 to B in case of duodecimal number system. We will repeat the same process. For hexadecimal, 0 to, we will repeat the same process. 16 minus 1, 16 minus 1 is 15, minus 1, 0 to 15 minus 1 is 15, so we have 0 to 15 all the way to 0, 1, F, all the way to 15. This was the small introduction on number system. This was the small introduction on number system. We will see more details in the coming presentations. We can also have a number system with base 4. We can also have a number system with base 4. And in this case, we can have base 4. We have, and in this case, 0 to 4 minus 1, 0 to, so we have 4 distinct digits, and they are, we have 4 distinct digits, and they are 0, very simple. 1, so if we know the base, if we know the radix, so if we know the base, if we know the radix, the different numbers in the number system. The different numbers. Now we will move to next part of this presentation. Now we will move to next part of this presentation, in which we will discuss weighted and unweighted codes. 3, 9, the number 7 can be written as 7,000s, can be written as 7,300s, 9 tens, and 2 ones. 9 tens. This is how we can write this 2 ones. Or I can write 7 this number multiplied by 10 raised to power 3 multiplied by 10 raised to power 10 raised to power 2, 3 multiplied by 10 raised to power 10 raised to power 1, 9 multiplied by 10 raised to power 1, 0. This is how we can write the number 7,392. This is how we can write the number 7,392. The weight of this position is 10 raised to power 0. The weight of 10 raised to power 0. 10 raised to power 1. This position weight of this position is 10 raised to power 2, and weight of this position is 10 raised to power, and weight of this position generally the coefficients 3, 7, generally the coefficients 2, 7, these are the coefficients 9, and generally the coefficients are written, and generally the coefficients are determined by their position, and the power of 10 is determined by their with weights on position. The number system call weighted number on position, and the number weighted number system in which there is no weight on the position, in which there is no weight on the position, we call unweighted number system. So the number system and codes we can categorize into two groups. We can categorize into 2 groups. The first one is weighted. The first one is weighted, and second one is unweighted. And second one is unweighted. In weighted, we have few examples. In weighted, we have few examples. First one is decimal number system. That we have seen here. Number system. The decimal number system. We have seen. The second one, the decimal number binary of course. The second one is binary of course. Octal, binary coded decimal, etc. These are the examples of weighted number system. These are the examples of weighted number system. Examples of unweighted system are gray code, XS3 code, XS3 code, etc. So this is how we can classify the number system. So this is how we can classify the weights on position. Now we will move to the next part. We will the last part of this presentation, in which we will compare binary decimal, we will compare and hexadecimal number system, octal and hexadecimal number systems. There is a quantity. There is a quantity. We are representing this quantity in a number system. We are representing this quantity with base R1 system. R1 is the base of number system. R1 and let's say capital N1, and let's say total number of digits is the total number of digits. Total number of digits required to represent this quantity. Required in this number system. This quantity. Let's say there is another number system. Let's say there is another number system in another number system, and the base for this number system is R2, and the base for this number system is R2 is the total number of digits. Capital N2 is the total number of digits, and to represent this quantity. For an instance, let's say R1 for an instance, let's say than R2. R1 the base R1 is smaller than the base R1 is smaller than the base R1 is greater than capital N1 is greater than important point. This is very important point. When we increase the base, when we increase the digits required to represent the quantity decreases. For example, the quantity decreases. 7392 is the decimal number which is used to represent the decimal number. Then in binary, the quantity. Then in binary, it is represented. The quantity is represented by. It is represented. The quantity is represented by 1110011 in binary. So you can clearly see the number of bits are way more as compared to bits are way more as compared to because base of binary number system is because base of binary number system base of decimal number smaller than the base of decimal number system. If I represent the same quantity 7392 in octal, then I will have 1 octal, then I will have 1 6 this is in octal. We definitely have reduced the digits. We definitely have reduced the digits, but we still have more digits system. But we still have more digits. In decimal, we are having 1 2 3 in decimal we are having 1 and in octal we have 1 2 3 4 and in octal we have 1 2 because in octal number system the base is 8 and octal number system 8 is smaller and still 10. 8 is smaller. Now we will represent the same quantity. Now we will represent the same quantity in hexadecimal. In hexadecimal it is equal to 1 in hexadecimal it is equal to 1 C. This is in hexadecimal 0. Now there is one important thing that you can see. Now there is one important thing that you can see. 4 digits. Here we have 4 digits, and so we can say that N1 is not strictly greater than N1 is not strictly greater than N2, but they can be equal.